Okay, so in today's lecture, I'm going to introduce some of the quantities we saw last time a little more formally. So we'll talk about observables with respect to continuous quantum states. I'll go over Schrödinger's equation for a free particle on a line more precisely, and then we're going to step on and talk about particle in a box, okay, which will give us a toy model, you know, a very simplified model in which we can actually talk about atomic qubits. You know, this simple model is surprisingly accurate, and it'll allow you to picture what a qubit might look like. Okay, so let's start. Let's you know, so our what we want to do is we want to model a particle on a line, and to begin with, we think of a particle which can be in one of a discrete number of states on the line. Say it's in one of these k different locations, and then of course we'd write the state of this particle as a superposition, sum over j of alpha sub j, where j goes from 0 to k minus 1. And we might also wish to create an observable which gives us the position of the system. So let's say we have a position observable M. So M is going to be a Hermitian matrix. So M equal to M conjugate transpose, and therefore it has an orthonormal set of eigenvectors with real eigenvalues. So what are the eigenvectors of this observable M going to be? Well, if it's a position observable, then the eigenvectors should clearly be the states of definite position, which is J. So it's a standard basis states, and M of course will be diagonal in the standard basis, and then what do we want the position value to be? So, well, we want it to be, of course, this matrix, right? So M times J, if we are in the definite state J, then it gives us this. The eigenvalue is also J, right? And so that's what it gives us. So for example, you know, if we happen to be in the state 1 over square root 3, 0 plus square root 2 over 3, 1, this is not a state which, you know, here the position of the particle is not definite. So if we have a 1,000 such particles, each prepared in the same state, and we measure each of these 1,000 particles, then roughly 1/3 of them, you know, roughly 333 will end, you know, when we measure them, they'll be at position 0. So the outcome would be 0, and for roughly 666, the position would be 1, right? Of course, if you want a definite outcome, we should be in one of the eigenstates, which is either 0 or 1 or 2, etc. Okay, so that's a quick recap of the discrete state of the events. And now, in the case of you know, in the case that we don't want these discrete states, but we want the particle to be anywhere on the line, then we replace this state vector psi, which is a finite dimensional vector, a k-dimensional vector, by a wave function psi of x, right? So think of psi of x as the amplitude of being at x. So psi of x is a function from the real line to the complex numbers. Okay, so now we have it's as though we are replacing this this k-dimensional vector psi, right, alpha naught through alpha k minus 1, by this infinite dimensional function psi of x. So think of k as becoming very, very large and continuous, and that's what this function is. And of course we must have a normalization condition, and that's given by the integral from minus infinity to infinity of psi of x magnitude squared dx equal to 0. We also have a notion of inner product. So we have an inner product. So if we have two different wave functions, psi of x and phi of x, then the inner product is just the integral from minus infinity to infinity of phi of x conjugate psi of x dx. So by the way, let me point out something that I guess if alpha is a complex number a plus ib, then we've been using the notation alpha star to denote a minus ib. It's the conjugate of alpha. And I'll also interchangeably use the notation alpha bar. So sometimes I'll use alpha star, sometimes alpha bar, depending upon which is convenient to write. And so you should interpret them to be exactly the same thing. Okay. All right. So now let's look at the fact that our observable M was Hermitian, which means that M equal to M conjugate transpose. Another way of writing that is, this is the same thing as saying the ijth entry of M. Right? Make sure you understand why this is the ijth entry of M is equal to, if you look at the jith entry of M, it's the conjugate of that. Now, you can also, this is also called Selfadjoint, and of course this holds not just for basis vectors I and j, but it actually holds for any two states phi and psi. So M is self-adjoint or Hermitian if and only if this holds for any two states psi and phi. Okay, so convince yourself that this really is trivially equivalent to the previous assertion. Okay, so what corresponds to a Hermitian, to a self-adjoint, to an observable in the finite dimensional case? Well, it's just it's just going to be some linear mapping on wave functions, right? So an observable is a linear function. It's self-adjoint. Mapping M that maps wave functions to wave functions. So for example, there's a position observable x hat, and the way x hat works is x hat, when it's applied to a wave function psi of x, it gives us some wave function phi of x, where phi of x is just x times psi of x. Okay, so where did this come from? So remember what we had for the position, if you had a position observable in the finite dimensional case, we wrote it down like this, right? It was, so where this was the position of the particle, it was at position 0, 1, or etc. And when we applied it to some state alpha 0 so on to alpha k minus 1, we just got a new state which was 0 times alpha 0, 1 times alpha 1, k minus 1 times alpha k minus 1. Right. So this corresponds to psi of x. Right? So at x, psi of x is the amplitude for being at that point. What does phi of x tell us? Well, phi of x is the observable applied to psi of x. And what should it tell us? Well, it should multiply that amplitude by the position, which is the eigenvalue of that, right? So these are the eigenvectors. So the position eigenvectors are x itself, right? 0 or 1, etc. Right? So the position eigenvectors are in this case are of the form j. And so j is so whatever is in this jth location, the delta function at j, it gets multiplied by j. Right? So you get j times alpha j. Yeah. And that's exactly what's happening with the position observable. And of course you can see that this is self-adjoint and it's Hermitian, etc. Okay, so the other interesting operator is the momentum operator, which is denoted by p hat, and it's I h bar d by dx. Okay, so what this means is that when you apply this to a wave function psi, so p hat when applied to psi of x is I h bar d by dx of psi of x. Okay, so let's try to wrap our heads around it and see, why is this a Hermitian operator? So the easiest thing to do is to just think about it in terms of the discrete analog. So let's try to understand the discrete analog. So again, remember we are thinking about it like this. We have a particle on a line. It's at one of a discrete. We have these evenly spaced points, and it's in one of these evenly spaced points, a finite set of them. And so we write our state vector as alpha naught, alpha 1 through alpha k minus 1. And now, how should we write the derivative, d by dx? Well, d by dx has the following interpretation. So to get the derivative at this point j, one way I can figure out the derivative at this point, if I have some function, is at x, I can look at the point to the right of it, x plus delta x, and look at the function value there. I can look at the point to the left of it, x minus delta x, and look at the value there. Take the difference and divide by 2 delta x. Okay, so what does this correspond to? Well, what it corresponds to, I claim, is if you have 1s on the off diagonal, 0 on the diagonal, and minus 1 below the diagonal. Okay, so why is that? Well, you see, because if you have let's say alpha j minus 1, alpha j plus 1, and now imagine what's it going to look like when you multiply by what's the jth row going to give us? Well, you'll take this vector and slide it along the jth row, and of course alpha j will multiply with 0, alpha j minus 1 with minus 1, and alpha j plus 1 with plus 1. So you'll get alpha j plus 1 minus alpha j minus 1, which is exactly what we wanted here. That's the first derivative. So this matrix corresponds to the first derivative. But is it Hermitian? Well, no, because if you take its conjugate, well, it's real, so conjugate does nothing, and when you take the transpose, you get negative of what it used to be. Okay, so now how do we make it Hermitian? Well, it's easy. We just multiply by I. So when we multiply by I, these get changed to i's, and these get changed to minus i's. Okay, and now what happens when we take the conjugate? Well, when we take the conjugate, the I gets replaced by minus I by I, and then when we take the transpose, we get back what we started from. So indeed, this matrix is self-adjoint or Hermitian, and so similarly, this momentum operator is self-adjoint. So this is something that you can verify. Okay, so now, having done that, we can start trying to piece together what Schrödinger's equation for a particle on a line should look like. Okay, so remember we had our momentum operator, p hat, which is I h bar d by dx. And now we want to understand what Schrödinger's equation should look like for a particle on a line. So we have a free particle on a line. And okay, so what Schrödinger's equation tells us is that I h bar d psi by dt equal to h psi. Right? Okay, so to understand what Schrödinger's equation says for this particle on the line, all we have to do is understand what h is. Well, what is h? H is the Hamiltonian. It's the energy operator. So what is the energy of a particle on a line? Well, the particle, classically the energy would be the potential energy plus the kinetic energy. In our case, the particle is a free particle. So we have a free particle, which means, by definition, that there's no potential energy. What about the kinetic energy? Well, classically, the kinetic energy is p squared over 2m, where m is the mass and p is the momentum. Okay, so now there's this heuristic way of guessing what the Hamiltonian is going to be for in the quantum case. So what you do is you do something which sounds a bit ad hoc, which is you look at the classical case and you replace your momentum by the momentum operator. Okay, and to make it sound very official and make it sound correct, physicists have invented a name for this procedure. They call it the correspondence principle. Okay, so using this correspondence principle, which is a nice way of guessing what this basic equation of motion should be, we'd get that I h bar d psi by dt equal to p hat squared over 2m times psi. So what's p hat squared? Well, you just apply p hat twice. So it's I h bar d by dx time of I h bar d by dx 1 over 2m psi. So that's really, if you take the derivative twice, it's a second derivative. I squared is minus 1, so it's minus h bar squared over 2m d squared by dx squared of psi. And this is exactly the form that we intuitively came up with last time. So last time we said, let's not worry about the constants, and we said Schrödinger's equation for a free particle should in form something like I d psi by dt is d squared psi by dx squared. And that's what this other way of looking at Schrödinger's equation also tells us.